Okay, welcome back to Real Analysis. We're going to start our work in Chapter 4 in this video lecture. So far in the course, mainly in Chapter 2, we've been studying sequences, real valued sequences. Those are just real valued functions whose domain is the set of natural numbers, the counting numbers, positive counting numbers. Now I want to turn our attention towards more general real valued functions, functions whose domain can be any subset of the real numbers, maybe an interval of real numbers, maybe the entire set of real numbers itself. Okay, and really for the rest of the course, we'll be talking about functions on such sets. So we need to spend a little bit of time here in chapter 4, kind of getting used to the nature of subsets of the real line. We're not just going to be working with the natural numbers, which is kind of a discrete set where the points in it are equally spaced apart, but rather more general sets. So for the first couple of sections, and mainly in chapter 4, we're going to study what mathematicians you kind of call the topology of the real numbers. We need to sort of understand sets of real numbers and how they behave, what kind of characteristics they can have. And in this first section, section 4.2, we're going to just mainly focus on points, elements of the real numbers, and how they are belonging to or nearly belonging to sets of real numbers. All right. So said a little bit more precisely, I want to establish some ideas about points in the real numbers and subsets of the real numbers. So chapter 4 is going to lay out these ideas, and in section 4.2, we're going to specifically look at different kinds of points that you can have in R, given a subset E of the real numbers. All right, so that's just kind of a little preamble here. Intervals are going to play a huge role in what we're doing. So let's kind of remind ourselves of the notation for intervals and some of the terminology. So if you take two real numbers, A and B, let's say A is less than B, then by the closed interval between A and B, which we denote in the usual way, just like in calculus with those square brackets, we just mean all the numbers between A and B, including A and B itself. And it's very important throughout this whole video. You should stop the video a lot and draw your own pictures. Try to visualize these concepts that I'm describing. So here I visualized a closed interval for you, and it's not a surprise. It's just the set of numbers between two given real valued numbers, including the endpoints. So those square brackets I'll even use in the picture to indicate that A and B both belong to that closed interval. Yeah, so very familiar. Likewise, the open interval between A and B, is denoted with parentheses. It's nearly the same set as the closed interval. It's just that the two endpoints, A and B themselves, are no longer in there. So we only look at the set of numbers that are between A and B strictly. So again, visualize that. It looks just like the closed interval, except there's no endpoints in there. All right? There are points in this interval that are so-called arbitrarily close to B, but B itself isn't in there. Same thing with A. Nice. Here's something we defined earlier in the course when we were talking about absolute value. I want to bring it back here. If you give me some real number y and a positive number epsilon, then a specific kind of interval centered around y with radius epsilon is called the epsilon neighborhood of y. So I'm going to denote it by that same notation we used back in chapter 1, n sub epsilon of y. And it's just the real numbers x that are no more than epsilon away from y. It's an open interval. It's the open interval from y minus epsilon to y plus epsilon. Right? The quote unquote deleted, or sometimes I'll say punctured epsilon neighborhood of y, it's basically the same set. I'm going to denote it by n star sub epsilon of y. And it's the neighborhood, the epsilon neighborhood of y, except you take out y itself. That's why it's deleted or punctured. So if you want to write it as intervals, you have to use two of them. It's the interval, open interval from y minus epsilon to y, union or together with the interval from y to y plus epsilon. And I've drawn a little picture here, of course, exaggerating, I'm making that big open circle there to kind of indicate that the element y is not in there. All right, so the deleted epsilon neighborhood of y is the exact same set as the epsilon neighborhood minus that one point, y itself. Okay, kind of useful tools for some of the definitions that we're going to make. So I have four concepts that I want to introduce to you here in this video lecture. Here's the first one. It's called the concept of being an interior point. Okay, so if you take some subset of the real numbers, E, we'll use that notation throughout this video lecture. So I'm going to call a point X that belongs to E. So it has to be an element of E. It's called an interior point of E if there's some open interval centered at X, that is, there's some neighborhood centered at X that completely belongs to E. All right. So I'm using in that neighborhood language. I like it more because I can kind of quantify it better. So an element X in E is an interior point of E if there exists, so it's an existential quantifier, if there exists some number C, it's positive, such that the C neighborhood around X belongs to E. So intuitively, a point is interior in E if it's completely surrounded, quote unquote, by points in E. All right, surrounded in the sense that there's some neighborhood around it, all of whose elements belong to the set E. All right. So let's look at some examples. Some of these examples I'm going to kind of go into more detail than others, but you should definitely, either with pictures or using the definition, even better, kind of convince yourself that these examples that I'm giving are sound. So here's the first one. I claim that every point in an open interval, here I'm not going to keep saying it, but anytime I write an open interval, I'll write it just this one time. I'm assuming that A and B are real numbers and that A is less than B. Okay, so just consider that part of the package. If I write the open or closed interval between A and B, I always mean that. It gets cumbersome to keep repeating it over and over and over again. So what's the first example? Well, it's just saying that every single point in the open interval is an interior point of that interval. Here I'm going to try to give you a justification of that, excuse me. Why is that true? Well, if you give me a point in an open interval, so you pick some X in an open interval, I can always measure the two distances, positive distances, B minus X and X minus A. I know those things are positive because X is less than B, but bigger than A if it's in the interval. And then just define C to be the minimum of those two numbers. All right, the minimum of two positive numbers is positive, and you can write out the inequalities if you want, but it's clear from the picture here. Where is that minimum distance in my picture? Well, the way I drew X, it looks like it's closer to B. So if I take that minimum distance right there to be C, that entire C neighborhood of X lives in the interval from A to B. So X was an arbitrary point, so it's interior. Kind of compare that to if you take, say, one of the endpoints, I'm picking the endpoint A, that endpoint A is not an interior point of the closed interval, right? It doesn't even make sense to say it's an interior point of the open interval. It doesn't even belong to the open interval, but it's not an interior point of the closed interval because for every radius, for every positive C, the C neighborhood of A is going to contain points that are less than A. I'm just going to point at my picture up here above. If you have a point that's less than A, well, it's not in the closed interval from A to B. So no such neighborhood can belong to that interval. Draw the picture. Moving along here, I've got three more examples that I've kind of written out. The set of natural numbers doesn't have any interior points. Yeah, if you pick any positive C and you look at the epsilon neighborhood centered at a natural number, it's going to contain numbers that aren't natural numbers. No epsilon neighborhood can live inside of a natural number, can live inside the natural numbers. Draw your own picture. A slightly more complicated example, the rational numbers don't have any interior points. Why is that? If you take some positive C and you pick a rational number, the C neighborhood of that rational number is always going to contain irrational numbers. We talked about that back in chapter 1. So if it contains irrational numbers, it's not a subset of the rationals. So the rational numbers have no interior points. Neither do the irrational numbers, for that matter. The last example is not super interesting, but I'll throw it in there anyway. Every real number is an interior point of R. Every neighborhood of a real number is a subset of the real number. So it's kind of a trivial example. Okay, so that was one of our four notions, interior point. Maybe you should stop the video and kind of think of some other subsets of the real numbers that you've thought about before and ask yourself, what are its interior points? Maybe it doesn't have any, like the rational or the natural numbers and the rational numbers. Maybe it's got tons of them, like open intervals, closed intervals. Okay, so continuing along, the second notion I want to talk about, in some sense, it's kind of almost an opposite of interior point. It's called an isolated point. So once again, we'll call our set of real numbers E. And if you pick a point that belongs to E, it's called an isolated point. If there's some C neighborhood, it's split across two lines there, it's unfortunate, whose intersection with E only contains X. All right. So again, I like this quantified version that I'll call an element of E isolated if there exists a positive C. So it's an existential quantifier again, such that when you intersect the C neighborhood with X and E, the only thing you get is X. All right. So it's sort of isolated away from other points of E. Of course, you can't ask for this intersection to be empty because X itself is going to be in both of those sets. So it's an isolated point if that's it. All right. So let's look at some examples. The open interval and the closed interval between two real numbers A and B doesn't have any isolated points. There are no isolated points in that. If you pick any element of those intervals, you can't take an epsilon neighborhood small enough to intersect those intervals in only one point. Yeah, it'll always have more than one point in it. I'll leave it to you. Draw a picture and write it out with some inequalities. Just use the order properties of R. On the flip side, every point, example 2, every point of the natural numbers is isolated. How to prove that? Well, if you give me a natural number, I'll take C to be, say, a half. You could take it to be anything less than 1, positive number less than 1. The 1/2 neighborhood of a natural number intersect the natural numbers is only that natural number. I've kind of drawn a little picture here in blue. I've drawn the 1/2 neighborhood of that natural number n. The intersection of that neighborhood with the natural numbers consists only of the number n. It's isolated. Q doesn't have any isolated points. That follows from the density of Q, yeah? If you pick a point in Q, if you pick some x in Q, a rational number, and then you take any, I should have called it C to match the definition, but I already wrote epsilon. Well, then that neighborhood, the epsilon neighborhood of X, it actually contains infinitely many rational numbers. From density. So no point in Q is isolated. Same for R. Same exact reason. R has no isolated points. Here's kind of a more interesting example, because you kind of maybe from the natural numbers, you think, okay, it has isolated points if they're sort of far from each other. Check this set out. Take the set of reciprocals of natural numbers. Every point of that set is isolated, even though the elements of this set are kind of getting arbitrarily close to each other. If you pick any one of them, I'm going to leave it to you to check out the details. You could take a C small enough that the epsilon neighborhood of one of those things only contained one of those things. So even though they're getting arbitrarily close to each other, any given one of them is spaced apart from the others in some sense. Okay, so that's 2 of our 4 notions. Let's just keep going. You should stop the video and think through those examples carefully. The third notion is an accumulation point. All right. And I'm going to call an element of the real numbers, not necessarily an E. So E can be some set of numbers. Here, this point can be any number. Maybe it's an E, maybe it's not. But I'm going to call it an accumulation point, or that's what this book calls it. I'm used to calling it a cluster point. So if you hear me slip up and say that, I apologize. I'm going to try really hard to keep using this word accumulation point. Provided that for every C, so this one has a universal quantifier, the intersection of the C neighborhood with X is it has infinitely many points. All right. So saying it another way, some real number X, maybe it's an E, maybe it's not. It's called an accumulation point of E if for every C, so this time we have a universal quantifier, So it has to happen for every neighborhood. That C neighborhood of X intersect E is infinite. I don't think it's going to show up in the actual homework. I'll have to check. Maybe it will, maybe it won't. But there's a homework assignment in your book. I think it's worth thinking it through. You can always, and I actually encourage you to think about more homework problems in this book than what I actually assign and ask you to turn into me. That's a pretty thin set. But homework 4.2.18, you can prove that an element of the real numbers is an accumulation point for E if and only if for every epsilon, the deleted epsilon neighborhood intersected with E isn't empty. So you don't have to, it's a handy condition. Sometimes it's kind of a pain to show that this intersection is infinite. But what is this saying? If for every epsilon, the deleted neighborhood intersects C somewhere, E somewhere, and it can't be X because X doesn't belong to the deleted neighborhood, then that would imply that there's infinitely many. And certainly if there's infinitely many, this other intersection is not empty. Right? So half of that if and only if proof is kind of trivial. Let's look at some examples. Going back to our open intervals first. If you take any element of an open interval, it's an accumulation point of that interval. Yeah. So are its endpoints. The endpoints of an open interval are accumulation points of the open interval, although they're not in there. So this points out that, yeah, you don't have to be in the set to be an accumulation point. I'm going to leave the details to you, passing more of this on to you. Okay. For that matter, if you ask yourself, well, what are all the accumulation points of a closed interval? It's exactly the closed interval. So here, if I kind of draw just a quick picture to sort of narrate what I'm talking about, if we imagine that closed interval from A to B, the usual picture. So what I'm saying is that every point in there is an accumulation point. If you pick an X in this interval, you could even pick it to be one of the endpoints. Then for every C, no matter what neighborhood you look at, the intersection of that neighborhood with this interval has infinitely many points in it. So it's an accumulation point. It's true even if you pick an endpoint. Yeah, if I pick an endpoint, every neighborhood has infinitely many points in it. But if I choose some point outside of that interval, it's not the case, right? The C neighborhood, say for an appropriately sized C of this point out here, it doesn't have any points in the interval. So it's not an accumulation point. So everything in the interval is an accumulation point, and if you're outside of the interval, you're not an accumulation point. Cool. The natural numbers don't have any accumulation points at all. I'll leave it to you to think through the details. The accumulation points for the rational numbers is the entire set of real numbers. Every real number is an accumulation point for the rationals. That again is basically a statement about the density of Q in R. You pick a real number, you draw an open interval around that real number, it's got infinitely many rational numbers in it. Right? So every real number is an accumulation point for the set of rational numbers. Our set E that was kind of peculiar above, that all of its elements, or not, that its elements get arbitrarily close to each other, although each one of them is isolated, it has an accumulation point. Its accumulation point is 0. It's actually the only accumulation point of that set. Yeah. So every neighborhood of 0 contains infinitely many elements of the set E. Nice. Okay, one more notion. That's the notion of a boundary point. So this time again, we take E to be our set of real numbers. You take a point. It doesn't have to be in E. And I'm going to call it a boundary point if every C neighborhood, every interval centered at X with radius C, has at least one point in E and also at least one point that doesn't belong to E. All right. So it's a boundary point if every neighborhood of you, you're a boundary point if every neighborhood of you contains a point in E and a point that's not in E. All right. So you're kind of on the edge. You're near points in E and you're near points that aren't in E because it's for every interval. The idea is that you can pick C to be small. So writing that out in kind of my neighborhood language, a point in the real numbers is a boundary point of E. If for every C, the C neighborhood of X doesn't belong completely to E, that is, there are points in this neighborhood that are not points of E, and that C neighborhood doesn't belong to E's complement. I'm just denoting the complement by R minus E. So that is, there are points in the neighborhood that are not in the complement. That is, there are points in the neighborhood that do belong to E. Cool. Let's just kind of surf through some examples and then we'll call it a day for this video. So the boundary points of the open interval and the closed interval are just the two endpoints. Draw the picture. Draw the picture. Every neighborhood of A, for example, contains points that are in the interval, that is to the right of A, and it also contains points that aren't in the interval, to the left of A, numbers that are less than A. And there are no other boundary points, just the two endpoints. They're the kind of guiding example, right? They're on the boundary of the interval. The boundary points of the natural numbers is the natural numbers, right? So if you take any neighborhood of the natural numbers, if I just kind of make a quick sketch of the real line here, here's my natural number n. Maybe I'll show you where the successors are to give the picture some scale. Then if I take any open interval, regardless of how big it is, any neighborhood of n, then that neighborhood contains points that are in the natural numbers. It would always contain n itself. It might contain others, like in the picture I drew, but it also contains points that aren't in n. So by definition, every point in the natural numbers is a boundary point of the natural numbers. It sits on the edge of them in some sense. All right. The set of real numbers itself doesn't have any boundary points. There are, if you pick, I'll just kind of recycle the picture above. If I pick a real number, well, every neighborhood of that real number is completely contained in the real numbers. It's not contained in the real numbers complement, which is empty. There's nothing in the empty set. So the real numbers themselves have no boundary. Okay. Every real number is a boundary point for the set of Q. They're the rational numbers. So the set of boundary points for the rational numbers is the entire set of real numbers. Because again, if you give me a real number and some positive number, that neighborhood contains both rationals and irrational numbers. So that is, it has elements of Q and it has elements that aren't in Q. So every single real number is on the boundary of Q. It's sort of hard to imagine that. It's kind of a messier boundary than the previous examples. Okay. So we introduced four notions in this video lecture. We introduced something called interior points, isolated points, accumulation points, and boundary points. And these four notions will play kind of a critical role when we go to understand the nature of sets and also functions on those sets. All right, thanks for listening.